After traveling a whopping 1.5 million kilometers, the James Webb Space Telescope finally reached its destination, the Sun-Earth L2 point. This journey wasn't just a straight shot, it involved a precise maneuver called MCC2, lasting less than 5 minutes but crucial for Webb's path. Picture this. Webb's speed only changed by about 1.5 meters per second, like a brisk stroll. But that tiny adjustment placed Webb into a huge orbit, more than twice the size of the Moon's orbit around Earth. Now, Webb's gearing up for a busy 6 months, filled with tasks like aligning mirrors, calibrating instruments, and finally, diving into its first science observations. But why all the fuss about L2? I mean, it's just a spot in space, right? And not even a spot with stuff in it. So how can Webb orbit something that's basically empty? Well, here's the thing. Empty spots in space are more common than you might think. When two big objects orbit each other, they dance around a common center called the barycenter. If those objects are heavy enough, the barycenter hangs out somewhere in between them. Like, we say the Moon orbits Earth because its barycenter is inside Earth, and Pluto and Charon, with similar masses, twirl around a point between them. So yeah, orbiting an empty spot isn't as weird as it sounds, but here's the kicker. L2 isn't just any empty spot. It's a special point in space that's outside the Earth-Sun system. Sounds confusing, right? Well, don't worry. Plenty of other spacecraft have made this journey before, like NASA's WMAP satellite and ESA's Planck and Herschel telescopes. And right now, Russia's Spectre RG and ESA's Gaia spacecraft are hanging out there too. So, while it might seem mind-boggling at first, orbiting L2 isn't just possible, it's a well-trodden path in the cosmos. L2 is a key player among the 5 Lagrangian points in the Sun-Earth system. But here's the cool part. These points aren't exclusive to us, they exist in any two-body system like Earth-Moon or Sun-Jupiter. Here's how they work. If you plunk a third object at one of these points, the gravitational tug-of-war between the big guys keeps the third object in place. So as the system moves, the third object goes along for the ride. That's why we love L1 for missions like the Solar Heliospheric Observatory facing the Sun and Discover facing Earth. And L2, well, that's prime real estate for cool missions like Gaia and Webb. Plus, both spots keep spacecraft in constant communication with Earth, no matter where Earth is in its orbit. But L2 isn't just any old spot, it's perfect for Webb's infrared astronomy because it can shield the telescope from the Sun, Earth, and Moon with just one giant sun shield. Pretty neat, huh? Now, there are a couple of things to keep in mind. Firstly, that third object at the Lagrangian points has to be tiny compared to the big ones. Luckily, Webb's a featherweight compared to Earth, let alone the Sun. But here's the catch. These Lagrangian points are kind of like balancing a marble on a perfectly smooth saddle. It's possible in theory, but super tricky in practice. Picture this. If Webb drifts even slightly off course from L2, it's in hot water. See, it'll start to fall either toward or away from Earth. If it drifts away, yikes. Bringing it back means turning it around and firing thrusters, which would heat up the telescope fast. And that's a big no-no. Webb's thrusters are only on the warm side to avoid cooking the telescope with their heat or exhaust. So yeah, staying put at L2 is a delicate dance, but one that's crucial for Webb's mission success. Here's a safer strategy for keeping Webb on track. We nudge it close to L2, but not right on top of it. That way, if it drifts back towards Earth, a quick thruster burn pushes it almost back to L2. This keeps Webb from drifting too far away, where we couldn't rescue it. That's why the Ariane 5 launch was set to slightly undershoot, giving Webb the chance to make these mid-course corrections. The journey wasn't just a straight shot. It involved some clever maneuvers to keep Webb on course. Now, being just shy of L2 brings its own challenges. At that distance, the Sun gets eclipsed by Earth, leaving Webb without its solar power. Sure, we could use nuclear energy, but that's a pricey and tricky option. Plus, there's another snag. Something called Coriolis forces would make Webb orbit around L2 in a tiny loop, needing even more thruster burns to control its path. And let's not forget about the Moon's pesky gravity, constantly tugging on Webb as it dances around Earth. So how do we make sense of all this? Imagine Webb feeling the pull of both the Sun and Earth, balanced just right at L2. But move it a bit away and things get wonky. The Sun's tug weakens with distance, but Earth's gravity really starts to kick in. Now, imagine breaking these forces into X and Y directions. Webb starts drifting, pulled more by its own momentum than gravity's grip. To get it back on track, we need to tinker with its position, nudging it closer to Earth to counteract that drift. But as it gets nearer, Earth's pull gets stronger, causing Webb to inch even closer. It's like a cosmic tug-of-war. In the end, it's a delicate dance to keep Webb in line. We're not just dealing with simple physics here, it's like solving a puzzle in motion, with forces pulling and pushing in every direction. But with careful planning and some clever maneuvering, we keep Webb on its cosmic journey, unlocking the secrets of the universe one step at a time. We can't risk Webb getting pulled too close to Earth, or else the sun shield would be overwhelmed by the intense heat. But we've got a trick up our sleeves. We give Webb a sideways shove, countering Earth's downward tug. This sets Webb on a new path, swirling in a circular halo around a spot we'll call L2'. Here's the twist. Webb isn't attracted to a physical mass at L2'. It's actually just Earth's gravity pulling it in a sideways direction. Now, this is just the tip of the iceberg when it comes to Webb's orbit. We kept things simple to understand the basics, but the real deal is far more complex. So instead of launching Webb straight to L2, we aimed for a point nearby. Then, just as it started to drift off course, we fired up MCC-2 to lock it into orbit. This tilt gives Webb some room to move, following an elliptical path with highs and lows. At its farthest, Webb swings out 832,000 kilometers from L2, way beyond the Moon's orbit. In space, every move counts, and JWST's orbit is no exception. Efficiency is the name of the game, and this massive orbit ensures smooth sailing for our cosmic explorer. By staying far from Earth and the Moon, JWST avoids pesky shadows, guaranteeing uninterrupted observations of the universe's wonders. But hey, it's not all sunshine and starlight. JWST faces its challenges, like dodging stray light and staying in touch with Earth. With precision adjustments and nimble maneuvers, JWST stays focused on its mission, unlocking the secrets of the cosmos one observation at a time. Check out the next video on JWST doing amazing things in space from the I button of our channel. Hit that subscribe button and stay tuned for more thrilling updates from the depths of space. Together, let's explore the universe and uncover its hidden mysteries. See you in the stars.